Welcome to the ePathshala lecture series in computer science. We are dealing with the course computer architecture. So this module discusses about exploitation of ILP with software approaches. This is in continuation to the previous module that we looked at. So the previous module we looked at loop unrolling and we saw how instruction level parallelism can be exploited using loop unrolling. So now we are going to look at some more techniques using software which can also help exploit the instruction level parallelism. So we look at software pipelining, predication and software speculation. So loop unrolling, what we discussed in the previous sessions, and static prediction are the fundamental approaches that the compiler uses to exploit instruction level parallelism. And apart from that, you can also do code reorganization where the dependent code is shifted, moved across so that you reduce the dependencies and do a better scheduling. Now this module we are going to look at software pipelining, predication and software speculation. Now what is meant by software pipelining? Software pipelining is yet another optimization that can help improve the loop execution performance. So what we try to do here is we pick instructions from different iterations of the loop which are dependent on each other, and you try to pipeline them, try to form a kernel with these different instructions which form the loop of the loop body, instructions of the loop body. For example, if you look at the key idea here, we basically try to increase the performance by scheduling instructions from different iterations into a single iteration of the loop. So what we try to do here is the advantages of you doing this is it requires fewer registers than loop iteration for loop iteration than loop unrolling, because we pointed out earlier that one of the major drawbacks of loop unrolling is that it requires a lot of registers and that leads to register pressure. Whereas in the case of software pipelining, we require fewer registers per loop iteration, and it also requires some extra code to fill in the pre-header or the preamble as you call it, or the prologue, and to drain where you look at a post header or a post amble or an epilogue in the software pipelined loop. So we just like how we have a pipelining happening in hardware, we are trying to do a software pipeline. And just like how the hardware takes some time for the pipeline to get filled up, you get maximum throughput when the pipeline is fully filled up. And when you have completed all the instructions, it takes some time to drain the pipeline. In the same case here also, you are doing a software pipelining of the loop. So when all the instructions of the loop are executed in the loop body, you say that is the kernel and you get the maximum performance. But before executing the kernel, you need some time for the pipeline to fill up. So that is called the pre-header or the preamble or the prologue. And similarly, after you have executed all the kernels which correspond to the different iterations, finally you will have to drain the pipeline, which is called the post-amble or epilogue or the post-header. So just look at an example here. We look at a simple loop and its assembler equivalent. So say for example, you have a load instruction. You add some constant value to the data that is loaded from memory and you are putting it back into memory by using a store instruction. And this is executed by a number of times, by using the loop maintenance code, which is your subtract instruction and a branch or not equal to. So till the condition is satisfied, you have your loop getting executed. So you have a sequence of data taken from memory, a constant value added to it and the result put back into memory. Now this, as you can see, there is a lot of dependence in this body of the loop. There are 3 instructions which form the body of the loop, and the other 2 instructions are basically loop maintenance instructions. So if you look at the second instruction add, it is dependent on the load instruction. Similarly, the third instruction store is dependent on the add instruction. So each instruction is dependent on each other. So it is not possible to uncover parallelism here because there are only 3 instructions and all of them are dependent on each other. So that's why we looked at a loop unrolling technique earlier, where you unroll the loop and try to schedule different iterations of these loops in different slots so that the dependent instructions are separated. Now we are trying to look at a different concept here. For that, we look at an example here with the given latencies. So, let us assume these latencies between the different instructions. Now, assuming these latencies, if you try to schedule this loop without bringing in any of the concepts that we have looked at, you know you have to schedule the load instruction first, and because you need to have one latency between the load and the dependent add, you have to have a stall in between, and between the add and the store instruction, as you can see from the previous slide, we have assumed 2 clock cycle latency. So, you have 2 stalls, and similarly between the subtract instruction and the branch instruction, there is a data dependence again. So, you have a stall there, and the branch instruction, assuming that you have a branch delayed slot, that is indicated as a stall. So, this instruction takes, this iteration takes 10 clock cycles to execute. Now, what are we trying to do in software pipelining? So, in software pipelining, what we do is, if you look at pipelining these instructions, you know that each stall is equivalent to a no-op, and we could obviously be performing useful instructions in these slots. So, what we try to do is, instead of wasting those slots, we try to insert instructions from other iterations or different iterations to replace the no-ops, so that those no-ops are getting usefully utilized. So, what we try to do is, we unroll the loop body with an unroll factor in it. Let us assume that we unroll it 3 times. So, you unroll the loop 3 times, the same concepts of unrolling that we discussed earlier hold good, and then we select the order of instructions from different iterations to form the pipeline. So, for example, our loop body here consisted of 3 instructions, a load instruction, an add instruction, and a store instruction. So, you pick the load instruction from a particular iteration, you pick the add instruction from a different iteration, and you pick the store instruction from a third iteration. So, only when you have instructions picked from the same iteration, the add is going to be dependent on that load and the store is going to be dependent on the add. Now, if you pick these instructions from 3 different iterations, they are obviously going to be different. They are not going to be dependent on each other. They are going to be parallel instructions. So, we try to form a body of the loop picking up instructions from different iterations, and this is the pipeline that is formed. Say for example, that has been illustrated here. So, you can see that the loop has been unrolled 3 times. So, you have 3 loads, adds and stores indicated as iteration iteration I plus 1 and iteration I plus 2. So, we are unrolling the loop, that is the first part. The second part is we will have to select instructions. Now, these 3 iterations will be collapsed into a single loop body containing instructions from different iterations of the original loop. So, you pick load from one iteration, you pick store from one iteration, and you pick the middle instruction add from a different iteration. So, this has been illustrated here. So, we pick the store instruction, for example, if you pick it from iteration I, then the add is picked from I plus 1 and load is picked from I plus 2. So, that is how you form the kernel of the loop. So, that is the selection of the loop. So, each of these instructions are picked from different iterations, and if you can see, if store is picked from the ith iteration and add is picked from I plus 1 and load is picked from I plus 2, then what happens to the load and add instructions of I? You have not included it in the loop. Similarly, what happens to the load of iteration I plus 1? So, and what happens to the add and store of iteration I plus 2? Now, these instructions which are actually left out, these instructions will form your preamble and the postamble. So, whatever instructions are left out initially in the initial iterations before you form the kernel of the loop, that will come as your preamble. Then all the entire body of the loop, when you construct it into a kernel, that is when you get the maximum speed up, where all instructions can be executed in parallel because they are independent instructions. And finally, when you have finished executing the kernel, say for example, you finished executing the load of the I plus 2th instruction, and your add and store are still remaining, that will have to be executed separately. So, that will come as your postamble. So, that is the concept of software pipelining. So, that has been shown here. So, the store is taken from I, add is taken from I minus 1, we are putting it the other way, and load is taken from I minus 2. Earlier we indicated it as I plus 1 and I plus 2. So, we are showing it this way. So, you paste instructions from different iterations into the newly pipelined loop body. So, this has been again illustrated here. So, that is called the initial instructions to fill the software pipeline is called your pre-header or preamble or the prologue, and the later instructions after the entire kernel is executed a number of times is your post header or post amble or epilogue. So, assuming we reschedule the last two iteration steps, our pipelined loop can run in 5 cycles per iteration under steady state when everything is fine, which is better than the values that we had earlier of 6 cycles, but it is definitely not as effective as the loop unrolling that we looked at, where we had only 3.5 cycles overhead. Now, this is a pictorial representation of it. So, you can see that the software pipelining can be thought of as symbolic loop unrolling, which is analogous to executing the Tomasulo's algorithm in software, because you know that the Tomasulo's algorithm basically did a loop unrolling in hardware. Here we are doing a symbolic unrolling of the loop, and because it is only a symbolic unrolling that we do here, you know that not too many registers are required, and that is why we do not have the drawback associated with loop unrolling, where a number of registers were required. So, this shows the complete schedule. It shows the complete loop with the postamble, preamble and the kernel of the loop. So, basically software pipelining does a symbolic unrolling where it reduces the code size, and it is also not does not cause too much of pressure on the registers. Now, to look at a comparison between loop unrolling and software pipelining, so this has been shown here. So, loop unrolling, you know that depending upon the number of iterations of the loop and depending on how many times the loop can actually be unrolled, you are going to iterate the unrolled loop a number of times. Suppose if you have 100 iterations to be executed, and the loop can be unrolled 10 times depending upon the availability of registers and all that. Now, the unrolled loop has to be executed 10 times. So, every time you execute the unrolled loop, you know that you will have loop maintenance code coming in for the unrolled loop, because it is an iteration that is carried out. Within the unrolled loop, you do not have any loop maintenance code instructions, but because you have different iterations of the unrolled loop itself handling coming into picture, you know that you are going to have loop maintenance code. So, you find that you have a number of instructions that get overlapped, keeps increasing slowly till it reaches the maximum value, and then when there is an overlap between one iteration and another iteration, again you have a decrease in the number of overlapped instructions. So, you find that is the overhead associated with your loop unrolling way of exploiting instruction level parallelism. So, the throughs are due to the overlap that is happening between different iterations of the unrolled loop. So, the unrolled loop does not run at a maximum overlap due to the entry and exit overhead associated with each iteration of the unrolled loop, because every time you enter an iteration, you will have to have the loop maintenance code, which brings down the number of overlapped instructions. A loop with an unroll factor of n and m iterations will incur value of n by n non-maximal throughs. Now, if you look at software pipelining, in contrast to whatever we had with loop unrolling, software pipelining, there is only one kernel where there are not a number of iterations which get executed. There is only one kernel where it runs at maximum speed, where all the instructions have been brought in, and only the preamble and the postamble are going to cause problems. So, that is the only place where you are not going to operate at the maximum level. So, there is only one overhead associated with your software pipelining. So, that is the contrast between loop unrolling and software pipelining. But software pipelining is a more complex technique. So, to uncover the software pipelined loop itself, the compiler has to be very intelligent, whereas loop unrolling is a more primitive form of exploiting instruction level parallelism. So, the complexity is still there compared to software pipelining, and the overheads associated with loop unrolling and software pipelining are basically different. So, the pipeline loop only incurs non-maximal overlap during the startup and drain, since we are only doing it, the kernel is executed only once with a number of iterations. So, we know that software pipelining is another method of very effective method of handling instruction level parallelism using the compiler support. In practice, however, it is a combination of loop unrolling, because we have already seen that software pipelining basically does only symbolic unrolling. So, it is a combination of loop unrolling and software pipelining that happens, because anyway in order to software pipeline a loop, you will have to do a symbolic unrolling process. So, this unrolling automatically becomes part of your software pipelining process. Now, we look at the next type of method of exploiting instruction level parallelism, but with the support of hardware. So, we look at how hardware can support the software in exploiting instruction level parallelism. So, here we are looking at two different techniques. One is conditional instructions or predicated instructions. The second one is software speculation with, of course, hardware support. Speculation is a concept that we have already discussed, where we predict the behavior of a branch, and based on the prediction that is done, we try to go ahead and execute the instructions. So, when the software tries to do a speculation, it does a static prediction about the behavior of the branch, and accordingly it schedules instructions in the most probable path of execution. So, that is what is meant by software speculation. So, now we look at these two additional techniques which can be used for exploiting instruction level parallelism. So, the first one is a predicated instruction. Predicated instructions are also called conditional instructions. Now, all of us know that the main problem with conditional branching is the branch overhead that is associated with it, because we do not know whether the condition is going to be true or false. So, we will have to wait for the condition to be evaluated, we will have to calculate the branch target address, and only then we will get the exact next address to be executed, to be fetched and executed. So, that gives rise to control hazards. So, in order to avoid the conditional or conditional instructions, and that which will give rise to problems, we try to bring in these conditions into the instructions themselves. So, the conditions or predicates, say for example, if you had a jump on 0, I had a jump on 0 or a branch on 0. What we try to do there is we check whether the 0 condition is satisfied and then decide whether the branch is to be taken or not. Now, what we try to do is this 0 condition is brought in as part of the instruction itself. So, the condition or predicate is introduced as part of the instruction itself, and it becomes a predicated instruction. Now, the advantage of using a predicated instruction is it becomes an instruction which is data dependent. So, we are eliminating the branches. So, we are converting the control dependencies that we had into data dependencies, and hence we potentially increase performance. So, what we try to do is you are getting rid of the branches. Whatever the branch tested for is brought as part of a condition into an instruction itself. The conditional branches are removed and the control dependence is transferred into a data dependence. To give you an example here, suppose if you have a sequence like this. So, if you have to check for some predicate x and then do a transfer between A and B, B operation C. So, you will have to perform an operation between B and C, and you will have to write it into A if some condition is satisfied. So, this is the requirement. So, now this will obviously translate into a sequence of branch instructions, where you will have to check for the condition and then jump to a particular place, or else jump to a different label. So, that is how it is going to be executed. Now, if you can replace it with a conditional instruction, this condition of checking the predicate value is brought into the instruction itself. So, if this predicate is satisfied, that instruction is executed. If the predicate or condition is not satisfied, that instruction is simply turned into a no-op. So, that is how a predicated instruction is handled. So, any predicate can be brought as part of the instruction. If the predicate or condition is satisfied, then that instruction will get executed. Otherwise, the instruction becomes a no-op. Say for example, if you have a predicate x and then you perform an operation B operation C, then say that if this condition is satisfied, then execute the instruction, B operand C and store it into A. Otherwise, this instruction will simply be turned into a no op. So, this is yet another example. Say for example, if your variable A is equal to 0, then you will have to copy variable T into S. So, this if we do not have support for predicated instructions, this will be translated into the code that has been shown here. So, you have a load instruction which loads variable A into R1, and then you check whether it is a 0 or not. So, if it is not equal to 0, branch on not equal to 0, you skip to label. If it is 0, because the condition says if it is 0, then variable T has to be copied to S. So, if the condition is satisfied, then you load variable T into a register R2, and the content of R2 is stored into a location variable S. So, this is how the original method would have handled this condition, and you know that you have a branch instruction coming in here. So, this branch instruction will give rise to control hazards. Now, this has been translated into a different code here based on the predicated instructions. So, now what we do is you have a load instruction, you also execute the subsequent load, but the load is you have to compare and nullify the instruction based on the value of R1. So, if R1 contains a value of 0, then you will have to execute the store instruction. If R1 does not contain a value of 0, then you will have to skip the store instruction. This is yet another method that has been shown below. So, you have a load of R1 with variable A, load of R2 with variable T, and the conditional instruction says conditional move on 0. So, it is a conditional move instruction, and the condition that you are incorporating here is a 0. So, if R1 contains a value of 0, then R2 is loaded in variable S. Suppose if R1 does not contain a value of 0, then this instruction is simply annulled. It is considered as a no op instruction. So, that is the concept behind a conditional instruction. So, as you can see, you do not have a branch instruction here. So, your control dependence has been translated into a data dependence, because you are checking for the content of R1, which is a data dependency that you have brought in. So, check for R1, and depending on that you are going to execute this instruction. So, again you have some drawbacks also because of this, because it has been converted to a data dependency. Unless R1 becomes available, you cannot really execute this instruction. So, there are still drawbacks in converting it from a control dependency to a data dependency, but it still overcomes all the problems associated with your branch instructions or control hazards. So, what are the limitations of this type of instructions? So, annulled predicated instructions, though they are annulled, they still take some processor resources, because you start executing the instruction, later on you find that the condition is still not satisfied, then you still have executed instructions to a certain level. Only thing, you probably have not done your register write or memory write. So, you still have spent some resources on that. So, that is another that is a drawback. Predicated instructions are more useful when the predicate can be evaluated early, because you know, if you have a complicated predicate and if it takes a long time to evaluate, it is dependent on some other instruction. Unless the condition gets evaluated, you do not know whether the instruction has to be executed or not, and the resources that you spend on it is going to be too much. So, it is better that you evaluate the predicate earlier itself. Now, the use of conditional instructions can be limited when the control flow involves more than a simple alternative sequence. So, if you have too many complicated alternative sequences, then it becomes a problem. Also, conditional instructions may have some speed penalty compared with unconditional instructions. So, these days you have a number of processors where these predicated instructions have been included. Some processors support only a few predicated instructions, whereas you have processors like Itanium where all the instructions have a predicated version also. So, predication is a very useful feature that has brought into the architecture. Now, we look at the next technique, which is basically compiler speculation. Now, when we look at speculation, all of us already know the concept of speculation, where you are trying to do a prediction on the behavior of the branch, and based on that, if it is hardware speculation, you try to execute the instruction beyond the branch, make use of a reorder buffer, and if something goes wrong, you try to flush instructions from the reorder buffer. Whereas, when you are looking at a software speculation, So, the compiler will draw a schedule based on the static prediction that is done. So, the most probable path will be the schedule that is given, and if everything goes right, you will get the correct result and you will also get it at an optimized time. So, when you try to do compiler speculation, the capabilities that are required are the ability of the compiler to find instructions that with the possible use of register renaming can be speculatively moved and that they do not affect the data flow. The other requirements are the ability to ignore exceptions in speculated instructions until it is known that such exception should really occur. Now, this may not be possible by the compiler alone, so you will have to take the support of the hardware. So, the compiler can do aggressive speculation only when it has the support of hardware. So, when you have an instruction which is being speculatively scheduled, and if that instruction raises an exception, the exception should not be handled, because it is probably raising an exception because of the fact that it has been moved elsewhere. Had it been in its original place, an exception would not be raised. So, you will have to look at both data flow for the correctness of the program, and you will also have to handle exceptions. Exception should be raised only when an instruction is no longer speculative. So, that has to be supported by the hardware. The third factor again has to be supported by the hardware. So, the ability to speculatively interchange loads and stores or stores and stores which may have address conflicts. So, such memory disambiguation may not be able to be resolved at compile time. So, you need hardware support to handle this. So, both these features the compiler requires the hardware support in order to aggressively speculate. So, in order to handle the exceptions, we try to look at different techniques. So, the hardware and the operating system cooperatively ignore exceptions for speculative instructions. This is the first technique. The second technique, speculative instructions that never raise exceptions are normally used, and checks are introduced at the actual location of the instructions where an exception should occur. That is the second method. Third method is you make use of poison bits. So, they are status bits which are attached to result registers. So, when a register is written by a speculative instruction and the instruction causes an exception, the poison bit is set. Now, if those values are being used by subsequent registers, the poison bits are being carried on. But when a normal instruction attempts to use the register, it will cause a fault. So, that is the third method. And you also have another method where a mechanism is provided to indicate that an instruction is speculative and the hardware buffers the instruction result until it is certain that the instruction is no longer speculative. So, these are some of the methods that the hardware gives support in order for the compiler to do speculation. So, now looking at the difference between your hardware and software speculation methods. In the case of hardware, it is possible for you to disambiguate memory references, whereas in the case of compiler based speculation or software speculation, you may not be able to do memory disambiguation at compile time. And hardware based speculation works better when control flow is unpredictable. When control flow is not predictable, it is always better to go in for hardware based speculation, because in which case the compiler will not be able to do too much of speculation. Hardware based speculation maintains a completely precise exception model even for speculated instructions, which is not possible when you go in for software based speculations. Similarly, hardware based speculation does not require compensatory code or bookkeeping code, whereas in the case of a compiler based speculation, we need to have alternate sequences. So, if this sequence goes wrong, we will still have an alternate sequence which when executed will still give you correct results, but you may not have optimized timing result. So, compiler based approaches may benefit from the ability to see further in the code sequence, resulting in a better code scheduling than a purely hardware based approach. So, this is a very important advantage of compiler based speculation, because in the case of hardware based speculation, we are just looking at a limited number of instructions in your instruction window, and we are trying to reschedule the instructions within that window. Whereas, when you are looking at a compiler based speculation, the compiler looks at the entire code. So, it can do local code scheduling as well as different techniques for global code scheduling, and it might give you a better schedule. So, hardware based speculation with dynamic scheduling does not require different code sequences to achieve good performance for different implementations of an architecture. This is another advantage. So, to summarize, we have looked at compiler based optimizations. We have extended whatever we did in the previous module with respect to loop unrolling, and we looked at two different techniques here. So, compile time optimizations provide a number of analysis intensive optimizations that otherwise could not be performed at runtime due to the high overhead associated with the analysis. So, we looked at compile based approaches which are usually limited by the inaccuracy or the unavailability of runtime data and control flow behavior. Compilers can reorganize the code such that more ILP is exposed for further optimization or exploitation at runtime. So, it is not that we will have to only look at compiler based optimization. The compiler does an analysis and gives you a code. On top of that, you can try to look at exploiting more ILP using hardware approaches. So, compilers can also look at speculation with support from the hardware. Predication also definitely helps in exploiting instruction level parallelism. So, the most efficient approach of course is not just looking at a compiler based approach alone or a hardware based approach. It is a hardware software co-scheduling approach where the hardware and the compiler cooperatively exploit as much of information as possible within the respective restrictions of each of these approaches. Such an approach is most likely to produce the best performance. Thank you.